In activity 5.4, we're going to be sketching the graph of a of x based on what we know about f of x. Now right off the bat, part A says, what's the relationship between a of x and f of x? Well, by the second fundamental theorem of calculus, we know that a prime of x is this little f of x. This is the derivative of this function. So we're going to use that information when we sketch this as we have in some of the other activities. Now first off, we're asked to find a of 1, and a of 3 exactly. Now a of 1 is going to be the integral from 2 to 1 of f of t dt. Now what we'll do is first we'll switch the limits, so we're actually going to do 1 to 2 of f of t dt. So that's the area right here. So we have a quarter circle of area 1, which is pi over 4, but notice we had to make it negative to flip our limits. So it's negative pi over 4 is a of 1. It also asks for a of 3. We're going to be finding all the values, so we'll keep going with this. So 2 to 3 of f of t dt is equal to 2 to 3 is a triangle. Notice it's underneath the x-axis. It has an area of 1/2 because it's got a base and height of 1/2, so it's a negative 1/2. So we can start looking at the accumulations so that we can actually sketch the graph of a of x. So let's find some more values. So a of 0, it's the integral from 2 to 0 of f of t dt. And what we'll do is we'll make it negative and swap those limits, 0 to 2 of f of t dt. And remember, we already found 1 to 2, so we actually only need to find 0 to 1, which is a half, but it's going to be made negative. So it's negative 1/2 minus pi over 4. And so let's start plotting some of these points. So at 0, we are going to be a little bit below negative 1. So let's make this negative 1 here and positive 1. And this will be 1, 2, 3, 4, 5, 6, 7 along our x-axis. So we're going to be somewhere down here when we're at 0. It's around negative 1.25-ish. A of 1 we've already found. A of 1 is negative pi over 4, so it's going to be here. Let's go find a of 2. A of 2 is an easy one because it's 2 to 2 of f of t dt. Once those limits are the same, it no longer matters what your function is. Automatically, it is 0, so we can put that point in. A of 3 we've already found. It's negative 1/2. So that's about right here. A of 4, we're doing from 2 to 4 of f of t dt. Now remember, we already found 2 to 3 right here. So it's a negative 1/2 plus the accumulation from 3 to 4, which is negative 1. So negative 1/2 minus another 1 is negative 3/2, or negative 1.5. So right here's our point. Next thing we got is a of 5. So 2 to 5 of f of t dt, and going with our accumulation theme, it's negative 3/2 because that's going to cover 2 to 4, and then additional what we have from 4 to 5, which is another negative 1/2, so negative 2. So we're going to go a little bit lower here, and right there. Now notice, as we're sketching this, we have what looks to be a max here at 2. It makes sense because the derivative is 0 here, and it went from positive to negative. Here, derivative is 0, went from negative to positive, decreasing. We're probably going to have a min, and we're going to start going back up here when we calculate a of 6. So 2 to 6 of f of t dt. Well, it's going to be negative 2 because we have that accumulation from 2 to 5. And now we're going to go an additional 5 to 6, which is plus a positive pi over 4. So that's going to put us just about right here. If we wanted to, if we wanted to be more accurate, we get those as decimals, but we're just trying to get an idea of what the graph looks like. Finally, a of 7, 2 to 7 of f of t dt. equals, we're going to accumulate another pi over 4. So negative 2 plus pi over 4 plus pi over 4, or negative 2 plus pi over 2, which is just slightly on the negative side here at 7. Now, let's pay attention to what's going on. Our derivative is increasing from 0 to 1, so it should be concave up. And now it's decreasing, so it should be, our function should be increasing but concave down. Still decreasing, so still concave down. Constant derivative, so it should be linear. Increasing rate of change, so concave up. And increasing rate of change, so concave up. And then decreasing rate of change, so concave down. Now, what's interesting is we drew a graph like this earlier in exercise 5.1. And I just wanted you to see what's happening. We just have a vertical shift of our function because they all have the same derivative. This is the sheet that I had used earlier in that video. They all have the same derivative. They're all giving the same original function, just vertically shifted. So let's say we wanted to, let's do just one other. We wanted to do some function, we'll call it b of x, where it's the integral of 3 to x of f of t dt. The easiest way to do this without doing a lot of work is when x is 3, this thing is 0. So that tells me 1, 2, 3. There's that one, and now it's just going to be a vertical shift. You can see it moved up by about a half, so all my points are going to go up by about a half. And I'm going to be able to sketch a very similar shaped graph. So there's y equals b of x. Similarly, let's do one other. Let's say we had this is all from the last part, c of x, which equals 1 to x of f of t dt. So this tells me the 0 is going to happen at 1. So this is going to be a shift upward by, it looks like about a little over 1.5 of all my points, or we could even just shift the blue graph up by just a smidge. And we'll go ahead and draw our curve through those points. So that's how we can use this idea of accumulation in the second fundamental theorem of calculus to come up with an original function given a derivative, and in this case even a family of functions. It changes based on what our lower limit is.